Right. So now that we've gone through all the chemistry stuff, we've talked about water, we've talked about acids and bases, let's really start to get into meat and potatoes of this unit, which is biochemistry, or the study of the chemistry of living things. And like I said at the very beginning of the unit, we're going to focus on organic molecules and organic chemistry as we go through this. So there are 4 organic compounds that we're going to be looking at: carbohydrates, lipids, proteins, and nucleic acids. And we're going to look at how those are built and the functions of each of those as we go through the unit. An organic compound. So what does organic mean? Organic means, you probably have heard that before. Maybe you see it at a store and you think, okay, they're not using chemicals as fertilizers or something like that. That's a different type of organic. Okay, organic for us is when something is carbon based. Carbon based means there's this thing called a carbon skeleton, which I'm going to show you a lot of pictures of. And that's really the basis for what makes all 4 of those organic compounds that you see there at number 1. So bonds between carbon atoms and stuff being built off of that. They have specifically carbon-hydrogen bonds. Okay, carbon's bonded to hydrogen all throughout this organic compound. Now, what are these? It's not just carbon and hydrogen. We also have all this other stuff here too. So if you can remember from chemistry, or excuse me, from physical science, what do these things mean? C is carbon, H is hydrogen, N is nitrogen, O is oxygen, P is phosphorus, S is sulfur. Now those first 4, carbon, hydrogen, nitrogen, oxygen, are really the biggest parts of these things. And actually the biggest parts of living things are those first 4 elements. But then obviously phosphorus and sulfur are very big as well. Inorganic molecules are non-carbon based. Okay, non-carbon based. Now we can also go back to organic and say, okay, that's the basis of living things. So we'll talk about examples of those. But organic is life. Inorganic is non-carbon based molecules. So I don't have these carbon-hydrogen bonds or this carbon skeleton. A great example of that is something we discussed in a previous video, which is water. Water is made of 2 hydrogens and an oxygen. You don't see carbon in there. It's not carbon-based. So that is an inorganic molecule. Inorganic molecules can have carbon in them. It's not saying that they'll never have carbon. They're just not going to be carbon-based, and they will not contain a carbon skeleton. So here we go, organic versus inorganic. You see on the left there, that's an organic molecule. Notice I have this skeleton, this kind of framework of carbons, and then I have stuff built off of it, right? That's organic. Inorganic, well, that's my water. I don't have carbons over there. Now, what is it that makes carbon so important? Well, first of all, carbon has 4 valence electrons. Now, if you remember from our chemistry discussion, there's a magic number of 8, right? Atoms want to have 8, want to have a full valence shell, and they're going to do everything they can to fill up that valence shell. So if there are 4 valence electrons in this carbon, that means it can form 4 other bonds, or it can form double or triple covalent bonds where they're sharing more than 1 electron. And it can bond with a lot of stuff. You see there, it can bond with hydrogens, oxygens, phosphorus, sulfur, nitrogen, or also with other carbon atoms to form single, double, or triple covalent bonds. Basically, it can form this big skeleton. It can form a ton of bonds, and it's very versatile in how it does it. Now, it can also be in these big long chains or rings, which I'm going to show you in a minute, and it forms a carbon skeleton. Skeleton or framework. Now, when I say framework, think of like the studs in a house. You put these 2x4s up in your house, and then you attach everything to them. You put the drywall up, and you run your wires through them and between them and everything. Well, the carbon kind of is like those 2x4s. It forms a framework or a skeleton for everything to be built off of. And like I said, it can form long chains or rings. So I have a few examples here. This is a pretty simple one over here, right? If you see a double line like that, and we'll discuss this more in class, but that is a double covalent bond. And then I have it forming bonds with the hydrogens out here. Every line is a bond. Every line is a bond. So we want to have 4 lines coming off of each carbon. So if I count 1, 2, 3, 4 lines coming off of that carbon right here, let's focus on this carbon. 1, 2, 3, 4 lines coming off of that. Okay, that shows us that it has filled its valence shell. So I can form long chains. This is a long carbon skeleton chain right here. This is a carbon skeleton ring right here. So it's very versatile in how it can bond. Forms a lot of cool stuff. Okay, right down there at the bottom left, I have sugar. I'm going to talk a lot about sugars. That's a diamond in the middle. Diamonds are made entirely from carbon. Okay, and then that's coal down there at the bottom right. And coal is a remnant of things that were living millions of years ago, so it's carbon based. Again, just another review of a carbon skeleton here. Says it's the framework that allows large complex molecules to be built off of it. All right, so it's not always just going to be hydrogens. Anything that's made of just carbon and hydrogen is called a hydrocarbon. We're not going to worry too much about that in this class. Now, that takes us to our next discussion here, monomers versus polymers. Okay, so we're going to talk about these carbon-based molecules, but then I got to put together a bunch of things to build large, huge, complex molecules. Okay, so we have monomers and polymers. A monomer, mono is one, single. Okay, poly is many. So monomer or one, it's a small molecule that I'm going to put a bunch of them together to make a polymer. Okay, so a small molecule that I build with. These monomers can be a bunch of the same thing, or they can be a bunch of different things when I put them together, and we're going to see a lot of examples of that. Polymers are basically when I link or put monomers together, I build a polymer. They can be long chains, they can be branching, they can form rings. Again, this is all stuff that we're going to see as we move through this unit. Every living cell is made of and has thousands of different polymers. Every living cell is made of these polymers. So here you go, a simple example. A monomer on the left, think of a Lego. I love playing Legos with my kids. When I put a couple of these Legos together, I start to build a larger thing, right? Well, the monomer is the individual Lego, and the individual Lego, the polymer would be, okay, built this huge thing, but it's still made of the monomers down here on the right. As we're looking at organic compounds, well, you see what we got there. Remember, I have proteins, carbohydrates, nucleic acids, and lipids as my organic compounds. These are the monomers that are going to make them up. Keep this table handy. It's going to be in the note packet that I give you. It's obviously on this slideshow. So monomers of proteins are amino acids. The monomers of carbohydrates are monosaccharides. The monomers of nucleic acids are nucleotides. And then lipids, they're going to vary some, but a lot of times they're going to be made of these things called fatty acids. We're going to learn what each of those things are throughout this unit. How do I build them? How do I take them apart? Well, first of all, there's this process called dehydration synthesis. Synthesis is always building something. Okay, I'm putting things together. I'm putting monomers together. Every time I add one monomer to a polymer, or I put two monomers together, I remove a water molecule. So you see here, we remove a hydrogen from one side, hydrogen and an oxygen from the other. That builds a water. I remove those, and that links these two things together. That's called dehydration synthesis. Think of dehydrate. I'm taking the water out. This is something that you are not going to be required to know for tests or anything like that in this class, but it is a very important process that you may see as you get to your higher level chemistry classes. All right. So to build a molecule, I dehydrate it. I take a water out. If I want to break a molecule apart, what do? I shoot water at it. It's kind of, and I know that sounds very simple, but if I add a water into a substance, okay, so right here I have this thing called sucrose, which is a sugar, which we call it a disaccharide because there's two sugars together. But if I add a water into it, okay, I can break this bond right here, and that will break it into two single sugars, a glucose and a fructose. Okay, I always say it's kind of like I have this little squirt gun. If I shoot this little squirt gun at something, at a polymer, I can break the bonds and turn it into its individual monomers. So hydrolysis is breaking bonds by adding water. Dehydration synthesis is building bonds by taking water out. And again, hydrolysis and dehydration synthesis are not things that you're going to be required to know for tests and assessments in this class. However, it's nice to know. And that is monomers, polymers, and an intro to organic compounds.